Hey, what's up, physics people? We're going to be going over the third example from the energy unit today. And this one's a little bit of a longer one. It kind of connects, forces and work and all that stuff. So let's get to it. We have a box that's being pulled at a weird angle. And it gives us all of this information with the problem. And the question is, what is the work done by friction on the box? Okay, so I sketched out the problem right there. You can kind of see what's going on, and the box is moving to the right. It's getting pulled by a force. They tell us that the force is 250 newtons, and it tells us at an angle of 37 degrees. So we can put 37 degrees right there. All right, and so first of all, it says, what is the work done by friction? So right away, I know, okay, I need to start with our equation for work. Okay, so what is my equation for work? We can get that from our equation sheet. We know that work is equal to the force being applied times the distance the object moves times the cosine of the angle between those two quantities. Okay, so now take a look at that little drawing right there. I have the box is moving to the right, and remember, friction's job in the universe is to try to stop things from moving. So friction is pushing on the box in the opposite direction, coming from the ground. So what that turns into is the friction force, and then the angle is 180 degrees because the direction the box is moving right here and the friction force are opposites. Right? So when cosine of 180 degrees, that right there turns into -1. And so we end up with the work done by the force of friction is equal to negative whatever the friction force is times the distance our box moves. Okay? So I know that. I know how far this box moves from the problem. What we don't know is what is the friction force. So now we need to solve for the friction force. And anytime you think you need to solve for the friction force, we're immediately thinking of the fun equation right there. Okay. Now it's important to remember, what are these things? This weird looking U right here called a mu, the Greek letter mu, that is the coefficient of friction. And then the capital N is for the normal force. Okay. Now this box is moving, so this would be a kinetic friction force, and this would be a coefficient of kinetic friction. All right. So if I need to solve for the friction force, they give us what the coefficient of friction is right there, 0.33. And so we need to do to figure out what is the normal force now acting on our box. All right. So now we're kind of switching gears. We're dealing with forces and everything like that. So before we do anything else, I know if I need to solve for forces, I need to draw a force diagram. So we're going to draw all of the forces acting on our box. And so we have those forces acting right there. Now what we need to do is, we have one force that's going at an angle, and that angle is 37 degrees. So we can break that force up into its components. That would be that force in the x direction, and then going up, it would be that force in the y direction. And when we split those components up, we now have this kind of revised, simplified force diagram. These are all the forces and force components acting in the x and y direction. All right. Now remember, our main goal for this is to solve for the normal force. So our ultimate goal is, what does this normal force equal right there? And so we can use, Newton's second law, and we know that this box is not accelerating up or down at all. So in the y direction, the net force is equal to 0. And so when we plug in all of our y forces, well, everything going up must be canceling out everything going down. So if I plug those two things in and I have everything going up, the y component plus the normal force must be equal in magnitude to the force of gravity right there. And then again, ultimate goal, solve for the normal force. So we solve for the normal force right there. All right. Last step is just kind of plugging and chugging with all of our numbers. And we end up with the, let's see, normal force is about 300 newtons. All right. So we have a normal force of 300 newtons. That was the goal to plug into the fun equation. So let's go back down here. Okay. And if I have the fun equation, and I know that mu is 0.33, we just found out that the normal force is approximately 300 newtons. Well, the friction force is then equal to 1/3 times 300. Friction force is going to be about 100 newtons. Okay, so that right there is my friction force. Now we know enough to finally plug that back in to our work equation. So when we plug all that stuff in, I know that work is equal to negative 100 newtons times a distance of, how far was this thing moving? Let's see, it is pulled 15 meters. So 15 meters. All right. And the work done by the force of friction is negative 1,500 Newton meters, or 1,500 joules, negative 1,500 joules. Remember, any one of those units is totally acceptable for this stuff. All right. Now, why is this negative? Because this negative sign means something. That means which direction is the energy being transferred, right? Remember, work is a change in energy. So if we have a plus sign, plus means that the system is gaining energy. And then the minus sign means that our system is losing energy. All right? So what this tells us is that negative 1,500 joules, friction is taking that much energy out of the box to try to make it slow down. So the reason why the box doesn't slow down is there is a force being applied to it, putting energy in, at the same rate that friction is taking energy away from the box. All right? So if you have any questions or want me to expand on this any further in another video or something, let me know in the comments. But otherwise, I will see you guys in class. Have a good one.